姚一晨，你要准时上课是不是？我给你一个工作，你3:50每次进来这边，加提前下课，准时下课，可以吗？可以吗？啊，不可以，不可以，但是你可以催我。哇哦，very nice of you。没有，我在专这。Yeah。比例的部分都哪一个什么？这个什么？可以啊，可以啊，可以啊，可以啊，可以啊。你要现在问还是？
现在也是可以啊，我不懂那一的不要这样子，不要找
wait 啦，let me open。Okay, so you got question on assignment, is it? Let's see. Okay, yeah, which part? 1.2, this part. Okay, yeah. So what about this part here? What you need to find? Proves that F is non-zero element. Degree and prove that there's a change of level with this scalar here such that for this case. Okay, so what you want to do is let's see something. So your function, right? Okay. Okay, wait, so your function has a degree. Yeah? So let's call it D. So meaning what? In this polynomial here, the highest degree term should be total degree, the degree. But the point here is, after you change the variable, right? I don't think the minus there is a. Okay, minus is because of this change of variable, this part here. There's a minus here because you make it a plus here. If you put a minus here, then here become plus. So this minus plus doesn't matter. So what's matter is, maybe inside your polynomial, right? Let me give you some examples. So let's say fx equals to xyz. So let's say this is fx yz, like that. Okay. But so the degree of f is what? Oh, sorry. Okay, so degree of f is 3, right? Okay. Degree of f is 3. Okay. Can you change your variable such that this new f here could contain maybe z to the 3, the term z to the 3, with some scalar maybe, or something. Huh? No. You need to change your variable. It's not substitution. It's not substitution, right? Well, I mean, like you just do x plus z, y plus z. This word, right? Yeah. Yeah. I don't know. You try. You try. Yeah. You try. But do you know what's the question asking about? Yeah. You understand? So after change of variable, if you change all the variable to x, then your 3-dimensional become 1-dimensional. Yeah. Any more question? Say again. Is degree 1 polynomial? Yeah. Yes. 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 Yeah. Yeah. Okay. Okay. If you really hit any obstacles here, actually these things are actually obtained from the books. So you can go and read the read. Yeah. If you don't know how to do, no idea. You could just go and read the read. Yeah. But don't copy. Write in your own word. Okay. Yeah, it's in the textbook actually. This question I get from the textbook. Okay. Yeah, any other question? Any other question? Lecture or your tutorial assignment? I put out the tutorial question, solution for tutorial 3, and then I put out tutorial 4. Hopefully, I will come out with assignment this week about affine varieties. Yeah. I think we still need a bit of time to go through affine varieties. Maybe need about 2 to 3 weeks. And then see how fast we can go with projective varieties. I think the maximum hour we will get to is 9 weeks for all these things, affine, projective, and then the basic. And then we're left with 6 weeks. Within the 6 weeks, we need to do, if can, ideally, we will do singularity. What else we do? Singularity, divisor, and intersection. Okay, depend how it goes. Worst case, worst come to worst, maybe we'll throw away one of the topics. Yeah. If can, maybe we just spend 2 weeks on each topics. If can. Okay. Okay. Yeah. Okay. So far it's this plain. I'm still writing the notes. Hopefully today, we'll get to some category theory. Actually, yeah, the actual, not actual, but using the language there. But in this course, we won't test on category theory, but to describe some very nice phenomenon happening in the algebraic geometry, it's nice to use category. Okay. Okay. Let's continue with where we left yesterday. So yesterday we spent time talking about these polynomial map, right? So we have a map between algebraic set B to W, which is called a polynomial map. Okay, so please recall what a polynomial map is. Okay, you can do this.
How about Jiayi? What's a polynomial map here? Okay, so if you say that you don't understand this course, cannot listen to what I say. This is the thing you need to take care of. If you don't even know what's the definition, how you understand, cannot. Those understanding is fact one. 假的不会定义你还懂什么东西，你什么都不懂的，你听的都是道听途说的，好像拜拜这样迷信，人家叫你信你就信。Okay, so what's the definition here? If cannot remember, it's okay. 不懂不用紧，去找出来，把它找出来。What's the polynomial map here? I think we still need to have more setup here. We need to know what's the dimension they live in, which affine space they live in. So for example, let's let V live in an n-dimensional affine space and W live in an m-dimensional affine space. Okay, so what's the map now? Yeah, what's this map? Can find out yesterday note. Lecture, which lecture is it? Lecture 9. Yeah. Who can help? We can help or not? What's the definition? How? If what? Is a polynomial map if? What's in the note? Can you read? Lecture 9. I think I uploaded already, right? You guys found or not? Moodle. Lecture 9. If what? If there exists a polynomial f1 up to fm an. What's this an here? Polynomial ring of n variable. Wait, I got a call. Hello? Hello? It's a scam. Okay. Polynomial ring of an such that for all p in V, you evaluate that at every point, you can write it as a component of polynomial function. Okay. Okay, so one thing I want to remind all of you, before you say that you don't understand this class, you don't understand what I say, I want you to build a good habit. What's the good habit here? Read notes, read definition. Okay. If already this sentence put in front of you, also you cannot read, what you expect. What do you want to expect? 读都不会，放一个句子在你前面都不会读啊，你还要会什么？我不明白。OK 吗 ？Just now I just asking you to get the note out, read it. That's all. OK， 我没有要骂你我没有谴责你我现在是在教你OK， 也不用骂我的，骂我也没有用，骂我没有用。OK， 我在教你怎样读书，现在。I'm teaching you how to study. Get the notes out, read it. 不要想有的没有的东西。As simple as that. Okay. Okay. So this is polynomial map, and then we left you as a lemma here. So what's the lemma here? So the lemma is a map. F from V to W is a
polynomial map if and only if the j component of this f is equals to some yj composed with this f here. Okay, such that this fj here is a polynomial function. Okay, it's an element in this coordinate ring here. So still remember what's this coordinate ring here? This is defined as what? A quotient ring. What's this quotient ring here? Huh? What's this quotient ring? KV. Huh? What quotient by what? So there are two dimensions here. Which one to pick? N or M? N. Okay, polynomial ring of n variables. Quotient by what? Quotient by the ideal that attached to this variety. Okay. What is IV? All the function that vanish at the point of V. Okay. Notice that there's something that I didn't tell you here. What's the thing I didn't tell you here? Huh? I tell you F. I tell you Fj. What's the thing I didn't tell you? Yj. What's Yj? What should Yj be? Where these Yj are the coordinate function. In which space? In which space? N or M? In the affine M space, which is the core dimension of your core domain. Okay. The dimension of your core domain. Okay. Do you think that this lemma here is quite straightforward? What does it say? Actually, if you have a f, okay, if you project in each coordinate here, all of them should be a polynomial function. Okay, defined on this V. Question? Any question? You believe what I say? Huh? Yeah. Yep. Hey, wrong again. Wait, stop again. Okay. Okay, I think I copied the wrong one. This, okay. Wait, so let me check. Does anyone know what happened to this notation? I think everyone should notice this mistake here. So what happened? This W is a variety, right? Okay, so it should live in some affine space, right? But this is a polynomial ring. Okay, so this should be a affine space. Okay. Okay, does people agree that this lemma is quite straightforward? Is it quite straightforward or not? If it is not straightforward, maybe you can say, what's your point? I will see where people did wrong stuff, maybe. Not very active. Obvious or not? 没有反应。也不 obvious 也 obvious. Sorry? So quotient quotient, yeah. Okay, good question. Okay, why is it living in this quotient ring here? Yeah. A valid question. Well, yesterday what we discussed about this quotient. I mean today, okay. Actually, right, let me give you an example. We supposingly to start with one example, but I forgot. So if you look at this circle here, yeah, give me a chance, give me a chance, give me a chance, give me a chance, okay, give me a chance. So let's consider this unit circle here. Okay. Well, this unit circle here live in where? Which affine space? A2, okay, 2 coordinate. Maybe, yeah, any K will do. So, well, let's define a function. Okay, what's this function here? Well, we can define this function to, let's say, A1, okay, sure. A1, which is just K itself. Okay, what do we do here? Let's just send xy to x square, y square. Why not? Okay. What does x square, y square do? Actually, you just compute the length of your point. Okay. Well, you can consider another function, right? G. Okay, what we do is, again, x squared plus y squared, but I'm going to add x squared plus y squared minus 1. Does this two function different or not? Are they different? They are different, actually. You're adding an extra thing. But on C, they are the same. Does it make sense or not? Okay, so let me write here. Not F not equal to G on the affine space, but F equals to G on C. Why? Because on C, what happened to this last part here? Just 0. This is what we mean from yesterday notation here. Okay, if you just evaluate at C, they are the same function. Okay or not? Okay, in fact, this function is actually a constant function on C. Yes. Or not? You always get 1. Because on the unit circle, the length is always 1. Actually, it's a constant function. So let me write here. It is just the constant function 1. Make sense? Yeah. Okay. Okay, so let's show this. Okay, let's show this. Why I leave it there. So well, I guess one direction is obvious, right? One direction should be obvious. One direction should be obvious. So if you know that this Fi, right, live in KV, if you put all of them together, it's just a polynomial. Okay, so the other direction, okay, let's show it. Let's put down the proof here. So well, I will draw some picture for you. So let's go from left to right. So let's say we got a map from V to W. Okay, and we got a Yj here, and this W live in M affine space. So what you do is you read out the J coordinate, right? Okay, you have J coordinate here. So what we define here as a Fj here is the composite here. Okay, we define this composite as this Fj. Okay, makes sense? Does it make sense? Okay, so if so here we note that we got this picture. So if F is a polynomial map, okay, what do we have here? we actually have FJP equals to FJP, okay, by the definition of polynomial map. Okay. In particular, Fj is a polynomial function. Okay. So polynomial function is the map from variety to ground field. Okay, map is between variety. Okay, so please be careful. And then the claim now is actually this guy, FJP here, will live in the coordinate ring of V. Okay. Okay, any question? No question? No. Yes. When? 用在哪里？在哪里？在哪里？要在哪里？要在每一个地方还是？嗯哼。啊，okay, okay, okay. Okay, so which place you think you need to add that? This part. You think that this have to be writing like this, is it? So let me put here. Mod of IV. Like this. I think this part don't need, right? Because this is just by definition. Oh, sure. I mean, yeah. Wait. Let me think. Oh, you mean that even here we need to put modulo F already? Let me think. So let me think. Yeah. Yeah, correct. But the point here is we have equality here already, right? So I think for this stage here we use equality. For this stage, I think it's fine. Yeah. Yeah. Well, I mean, okay, wait. Before that, so here, okay, here actually we are checking on points also. It's not function. We're checking on point. Unless I write something like Fj equals to Fj mod IV like that. Right. So the modulo happen in the function space, not in the number. Number is exactly equal. Okay, so give you a context here. So for example, here, right, we will write. Okay, let me bring up here. So here we will write that F is modulo G mod out the ideal generated by ideal generated by, okay, so we know the ideal generated already, so S squared minus 1 like that. I think this is what we will write. Make sense? Yeah. Just now one I think is equal because it's just number. So basically referring to evaluate at C, they are the same number. In this case, it's the same function. So yeah, if you like,
maybe I write f on c on xy equals to g on c on xy, which is equals to 1 on xy, which is equal to 1. Okay? Okay. Yeah. Okay. I think it's a good idea here to distinguish the equality happen in the function space or happen after evaluation. Yeah, it's pretty important here. Okay, but this part here, Adrian, you buy or not? You buy? Why? So where do you pick these polynomial from? This is actually a question. So where do you, AK? Yeah, the polynomial ring. Okay, we pick it from the polynomial ring. Yeah. And then we consider that they are the same up to some ideal. Yeah. So the difference between n affine space and KV here, right, is just that whether you see some polynomial as the same polynomial or not. Okay or not? Yeah. FJP mod? What do you mean? Yeah. This one? No need. Because every point you evaluate on IV, you should get 0. So you always plus a 0. Like that. You mean plus 0? Like this? Mod AB, yeah.
So it's already naturally IV, everything is IV tends to 0.
Okay.
Right, the mod is the thing.
You mean like this? Mod IV here? But just now we claim, right, we don't need to write this thing because this is just number, two number. Two number is the same. And there's no more IV here. More IV happen in the function space. Yeah. Okay. Okay. Right. Okay, and then the other direction is obvious. If you know that all the component is already is a polynomial function, then you put them together, obviously it's a polynomial map. Okay, so the other direction should be obvious. Okay, so the corollary is any polynomial map f from V to W actually can be written in the form of f1 fm with fi up to fm living in the quotient root. Okay, so basically what I told what's this two-stage thing doing is I told you that a polynomial map is something that you can express as a polynomial function, okay, in each coordinate. But in fact, you just need to consider up to modulo IV. They are the same, right? I give you an example already. Okay, these two are perfectly grouped polynomial map, but they are the same. Okay, they are the same. They are the same polynomial map. Okay, you just need to write out one representative. So these two belong to the same function inside the coordinate ring, where you just pick one of the representative is enough. Does it make sense? Makes sense, right? Okay. Yeah. If not make sense, you just feel free to ask. Okay. Lemma. A polynomial map in your calculus, right? You will show that or analysis, you show that it's continuous. Okay, similarly, it is continuous in the sense of Zariski topology. Okay, I reckon that some of you haven't haven't do continuity in topology yet. But what we're gonna use here is, if a subset of your core domain is closed, then the inverse image of this subset is also closed. Then F is continuous. Okay, so meaning inverse image of a closed set is closed, then this function is continuous. There's another version, right? Open version. If a subset, the inverse image of an open set is open, then this function is also continuous. But because we are working in a Zariski topology, it's a closed set topology, we'll use a closed version. They are equivalent. Okay, so it's very easy to see why. So what we want to do is we want to show that if Z in W is closed, then the inverse image is closed. Okay, still can recall what does a closed set mean in Zariski topology means? Algebraic set. Okay, so you need to satisfy some zero set property, right? So now, if we can write that set as a closed set, okay, closed set of some algebraic set. How should I put this algebraic set? Can I be a bit lazy or not? I don't want to write down the whole thing. I just say that it has to satisfy some algebraic equation here equals 0. Then, what's the inverse image? What do you think? What's the inverse image of Z here? If you want to demonstrate it as a closed set, right, you want to write it as a algebraic set. So what's the equation have to satisfy here? What do you think? What the pre-image means, so you got a V, right? And then you got a W, right? Okay. And then you got a Z here. So what's the pre-image here? F in the Z. These are all the points such that when you map across, you have to map into the algebraic set. Okay, so if you cannot see this, maybe you need to see this equality here. What is this? Y left hand side in the right hand side, Y right hand side in the left. Yeah, but when you think about it, is it clear or not? Whatever in this pre-image, right? If you want to map into Z, meaning what? Every point that you take here, you use F to go to Z. To stay inside Z, you need to satisfy all the algebraic equation. Okay, I think left to right is quite obvious. But how about right to left? Every point that satisfies this actually is the pre-image. Okay, yeah. So this is the set theory argument. Try and think about it. Try and write it down. Okay. So it is close. Okay. Try and write down. I didn't say to trivial, but this kind of argument is quite elementary. Okay. Try and write it down. Okay. Why left to right, right to left is all right. If you happen to found that one direction is not true, then this proof doesn't valid anymore. Okay, so try and practice write it down. Okay, why left to right, right to left. Okay, so this is the claim here. Yes. What's the difference between trivial and elementary? For me, I mean, well, very hard to say. What's the difference between trivial and elementary? I mean, for different people, right, obvious could mean different things. One thing that's obvious to you might not be obvious to the other. Okay, so trivial is the same. I think trivial has an attitude here. Something that's trivial to you, but that's not trivial to others. But elementary, right, should be, there's a standard for elementary for everyone. So meaning what? Meaning what? Like standard 1, you need to learn all these things. You need to learn addition first. Standard 2, you need to learn multiplication, something like that. Elementary means should be something that you learned before. Okay, trivial, obvious, these words kind of come with an attitude. And then this could be different viewpoint from different people. But whenever you see obvious or trivial in my notes, right? What it means, I define this word actually. So this word means that you just apply whatever you had before using definition, it will fall out. You don't need to do extra construction. No need to do some extra words. Okay. I think most of the max textbook means this actually. Okay, whenever they say trivia, obvious, there must be something very basic you miss. So you need to go back and read the definition again, or you read some examples again. Then the argument will follow actually. Okay or not? Yeah. So trivial, obvious, doesn't mean you don't need to do anything. But the thing that you need to do quite obvious. Okay, so let's see. For example, yesterday we give some examples already, right? So if you look at the parameterization, you know from calculus, right? These are all polynomial maps. Yesterday we have these examples here, and then we also have the other examples. Okay, they are not just polynomial maps. Actually, they are bijective. Okay, they are bijective, so you can find the inverse. Okay, so one exercise you could do is try and find the inverse. So in case you cannot find the inverse, then you prove me wrong. OK 嘛？不要相信我讲的话，明白吗？你要去检查 ，you need to test, you need to do homework. OK 了。So if you found out that 没有老师，这里没有 inverse，你跟我讲哦。OK，你懂我讲什么吗？因为有种人是这样的老师讲的东西whatever people say to you, you take it, but it's wrong but you don't know it's wrong then you have contradiction inside your heart or inside your mind. Then 你就一直跟你的 contradiction 过不去。So you are, how to say you are bothered by the contradiction. Why not the lecturer is wrong? Let the lecturer wrong Why not? You understand 吗？明白吗？不要跟自己的 contradiction 过不去。Okay, bring it up. Okay. Next. All right. So next, we'll prove a very important property of our polynomial map here. So let's take two polynomial map. Okay, and then let's take an arbitrary polynomial function. So does anyone know what's the difference between phi, f, and g? What's the difference here? The codomain of phi is pretty fixed. Phi in this coordinate ring means what? Where is your codomain? If you put point in W into phi, what do you get? You just get field, a number. Does it make sense? OK 嘛？还要提醒你吗？什么是 KW？ 再提醒一次。What is KW？ 来，那个子倩。Yes, quotient ring. So what's this quotient ring here? K adjoin x0, x1, up to some, let's say this depend on this W lah. Then quotient by ideal attached to this W here. So all the function that vanish on that. Okay. So you evaluate this, you'll get a number K. Okay, so for this phi here, we will define something called pullback. Okay, I'll tell you why we call it pullback later. So I mean for the words, right? English word pullbacks. 什么意思啊? Pull back. Pull and back. 什么意思？什么？讲一次。推回去啊？什么？你讲吗？推背。Pull back。推还是拉到底？多拉。多拉还是打嘞？啊？多拉还是打嘞？打嘞？有看过那个门嘛？有 pull 跟 push 的。多拉还是打嘞？啊，不懂的话，那个门开不了嘞，这个。Okay, pull back. Okay, yeah. So what are we pulling back? Huh? So let's see. So this F here. So we want to pull your F back. So we will define this F star. Okay, this F star acting on a polynomial function. Okay, polynomial function phi. Okay, such that this is equal to phi composed with F. And then this is a polynomial function in KB. Okay, check correct or not? Can compose or not? F going from where to where? V to W. Phi W to K. Okay. Everything is from V to K. So in KB. Okay, such that what? So this is the main picture you need to remember here. So you got a map from V to W called F. W to K, let's call it A1K here, call big phi here. Okay. And then you compose them. Do F and then do phi. This is called the pullback of F. Okay, pullback of F. So you make a pullback, pullback. Actually, you come out of pulling back the domain of phi here. Phi arises from W, start from W, but you pre-compose with F, then it start from V. Okay, no? Okay, so it's kind of like pulling back the domain that the function you inputted. Okay, no? Can you see now? W, this phi actually start from W, but if you pre-compose with F, then the whole map will start earlier from V. Yeah. Okay. This is a pullback of F. And such that this diagram will commute. So let's draw this commutative diagram here. All right. So there are a few things we can check here. So we will have this property, which we call the Functoriality property here. Okay, I haven't tell you what's Funtor. There's a word called Funtor. I will call this Functoriality properties. This is something that a Funtor should do. Okay, so what is this doing here? So if you look at the pullback of the identity, okay, if you look at the pullback of the identity, so let's say this F is identity. What can you do? Okay, if you pull back every phi here, what can you see? Phi composed with identity, what do you get? Phi, right? So meaning what? You send all phi to phi. So it is actually an identity on the KV ring. Okay, so you put any element of KV, give you back the element in KV again. Correct or not? Phi composed with identity is phi. Okay. So the pullback of identity is always an identity. Second is, if you have composition, okay, how does this composition add under this pullback here? Can you imagine? If you like compose again. So let's say you got VWU G here. Okay. So actually you will get F star composed with G star. Okay, the pullback of F star composed with G star. Swap all. Okay. Matrix inverse also like that, right? The inverse of a matrix. Okay. Last one. Yeah, last one. Last one is actually phi star is a ring homomorphism. Okay, so this tells you how it add on the elements in KV. Okay, it's a ring homomorphism. And actually, it is a K algebra homomorphism. Okay, so K algebra homomorphism tells you that how it adds on the scalar. Okay, scalar K. Okay, I guess let's prove these. Let's quickly prove these. Very quick, real quick. Okay, so let's split them into 3 segments. We do it one by one. Okay, so as we say just now, how to check the pullback of identity. So you check it on every element in your KV. Okay, so what is IV star G? Okay, how do we define this? It's actually just G pre-composed with identity of V, but which is just G. Okay, so you send G to G. It's an identity map. Okay, so you send G to G. You send G to G is an identity map on. Hey, sorry, why am I using G here? So I should use a phi here. Okay, so identity on KB. Because you send phi to phi. Okay. How about the next one? Anyone want to try this? Does anyone want to try this? Try this GF star on phi. 来，谁要玩？金盛，看一下。By definition, what's this star here? 前面还是后面？你的那个往前面或往后面吧？没有，就是说你要 compose 在前面还是 compose 在后面？后面吧。后面，后面哪一个是后面，哪个是前面啊？When I say pre-compose, usually I say compose before here. Here is pre-compose. Here is post-compose. Right. So pre-compose is because you need to do this first, right? And then you do the rest. So because our composition goes from right to left. Okay. So where do you put GF? Pre-compose or post-compose? Pre-compose, so we do GF first. Okay. And then so these are what? These are just composition of function. Then do we need our goal in the end? Should we start at the end? There's another trick you should learn in mathematics. You can start from the back also. I already tell you where you should run already. So you can start from the back. So this is phi, right? Okay. You work backward. How to work backward? Này. Yeah. Phi composite G. So you keep your F star of phi composite G. And then phi composite G composite F. Are these two equal or not? Why? Because the map is associative. Okay. Okay. Yeah. Okay. So you need to use that our coordinate ring is associative, but it's a ring, right? Cool. Okay, this is done. How about this one? Ring homomorphism. I just leave it to you to check. Okay, so you check that P star on phi 1 plus phi 2. What is it? It should be equals to phi star on phi 1 plus phi star on phi 2. So I mean in the middle, what should you pass through? It's just phi 1 plus phi 2 composed with f. Our composition should be distributive. Okay, so you cannot distribute it. Okay or not? Okay. Similarly, you check on products. Okay, you check on products. Here is products, not the composition. It's really a product. So I need to check that it's split into the pullback, the product of the two pullbacks. Okay, how to check a K algebra homomorphism? So one thing you need to notice is for every constant C here, what do we have on the pullback of this constant? What is the pullback of this constant here? So meaning constant composed with f. What does it do? Still going to be a constant. Send every point back to C again. Okay, no matter what f do, you send back to C again. Okay, so actually it's a constant. It's send constant the pullback. Okay, so this will tells you that f star is also a K algebra homomorphism. Okay, so the morphism that you need on your constant is this map here, preserving your constant. Okay. Okay, so the point here is, so the upshot here is every polynomial map f from V to W give rise to a K algebra homomorphism. Okay, how to give rise? So this f star here is going from where to where? Actually going from KW to KV. So you can see that actually swap. You can swap the variety inside this coordinate ring. You can actually swap. How to define? Still remember? So if you take this phi out, what you do is you assign it to phi and then pre-compose with f. Okay, so you pull it back. So you pull this W back to V. Because f start from V. Okay, so this is the thing you need to remember. If you have a map from V to W, on the coordinate ring, right, it goes the other way, KW to KV, because you have this pullback in. Okay, you pull the domain W back to V because your f start from V. Okay, your f start from V. Okay, any question so far? No question? 有问题吗? Yes. Where's what? What is upshot? What is upshot? 重点. Yeah, the main point here. 不用紧，不用紧，可以问的，可以问的，我没有讲什么，不要笑不要笑人舆论会害死人舆论。Yeah. Okay. Any question? Any other question? 还有问题吗？还有问题吗？好。OK， 我有一个问题。Ivan 呢？Ivan 在哪里？2天没有看到他。不知道。Okay, let's take a break until 5:10. Hey, yeah.
I have question.
Yeah.
Just now the lemma,
Yeah.
the continuity on the Zariski topology lemma.
This one, yeah.
Isn't this line satisfied by any f? Does it need to have polynomial map?
Thing, but if it is any map, right? Yeah, 什么什么？
我看
前面。
看那个对，看这个
You must show that you have any map. I mean, this argument any map will work. Okay, but I think one more thing you need to consider is because this is closed, if only this is a polynomial map. If your composition is not polynomial map, then it's not an affine algebraic set.
But then by definition, if all of these are zeros, doesn't that mean it satisfies those polynomial and therefore is algebraic set?
I mean, if you compose, right, if this is not polynomial, right, then this holding might not be a polynomial.
But that does not matter, right? Because it satisfies some polynomial, some function.
No. Affine algebraic set must be polynomial. Eh? Yeah, must be polynomial.
Algebraic set.
Yeah, must be
Polynomial, right? Otherwise, we prove that sin x is not algebraic, right?
KX.
Yeah.
它是个定义
Must be a polynomial. Yeah, you must get a polynomial. Yeah.
So definition.
Affine algebraic set
第二问就是有
require the function to be polynomial.
对，很奇怪啊，我看
Zero set of polynomial. Because we take from the affine, I mean, we take it from the polynomial ring. Correct enough. Yeah, but that's the good point to catch. Yeah, why the other function will work. You might get non-polynomial function. Then it's not affine algebraic set. Okay, all right.
我有个问题，你的这个第二个部分，
你看，
这个地方的范语是 KX 没拿吧，不是 KB 吧？
反了哈。
我觉得应该是 KX，你确认一下。
看先。
因为你就看这一个式子嘛，因为你 F 是从 B 到 W， 然后 G 又从 W 到了 X， 所以这是一个 B 到 X 的，所以这个范应该是活在 KX。
对。
我总觉得这有点虚符的味道。
对呀，我们要到虚符的一下。
这是个虚符。
这个还不是个虚。
有点像我觉得。这好像是个 ring space， 你看，因为虚符是把 open set 送到 F 里面过户，这边你把每个 close set 给它 map 到了一个 ring。
乱呢？
你在 OK， 等一下我们会讲这个概念。等下我们会讲这个。
乱了？
怎么？哪里乱？
你 F star 是把 polynomial 变成 polynomial。F
star 是把 polynomial function 变成 polynomial function 啊。对 ，polynomial function 变成 polynomial function。对，
这样，这个你是画错。
没有画错啊，没有画错啊。我是把 polynomial function 变成 polynomial function 了。
这是 A1K。
对啊 ，A1K 啊，对啊。polynomial function 就是 evaluate 在。
这是 evaluate 了的。这个应该没有 evaluate 的吗？
这个没有
evaluate。
没有 evaluate 啊 ，KV 就是 like KV 就是全部从 V 去 K 的一个 function space 其实。
KV 是 set of polynomials that is not trivial under ID。
对，但是它 evaluate 去 K 嘛，然后你放 point 进去，它就 evaluate 去 K 了嘛。
对啊。
KV 里面的东西就是一个 map 从 V 去 K 的 map， 对吗？
因为你以为它就会变成去 K 啦。B 是 KW。
对呀，这个，但是这个可以适合你看，你看到那个，那个不行，看起来那个对应该是挺，
六七 A，你要 evaluate 它，所以这里不止这样少啊，因为这里还有一个三角形，这里又有一个三角形。对呀、这你要通过 KW 再去这里。
我总觉得当你把一个 function 作用在一个 function space 上的时候，是真的容易绕晕。
因为不习惯嘛，
对，
啊，因为不习惯，因为通常人家想两个方向就是把它 combo 在一起就是了。
但是你现在真的把一个 function 作用在一个 function space 上，
对，应该要把那个方向想成一个点。
对，但是就感觉对于我们这些初学者就很难想。
肯定。
你画 diagram 出来是 KV、KW 全部隐藏在里面。
是啊，就是说这条线 KW，这条线是 KB 哦，
应该要讲，
这条线。
应该讲这条线只有 KW 的东西才会有 non-trivial。
哦。如果你要我加这个进来的话，可以这样加，就是 like 这个东西是在 KW 里面，另外一个东西是在 KV。对，那把这两个加进这个图里面。
所以基本上是在 composition 啊。
对。
我想这样，我们卡在那个的 normalization， 我们在想那个 k 是不是infinite 那个，还是 finite 也要讨论。
没有吧 ？Algebraic close 了是吗？
你在第一才讲，你在第四才讲Algebraic。
是咩？给我想想，
就是第三没有去讲的话，
重要吗？你觉得？给我看一下。
我刚才就读了一下，我有个小问题。
应该就是小题接小。
话说你的第一小题这边是 Victor，
你讲3去4还是4还是哪一个？3我不是 infinite field
3的 k，
不是 infinite field 了没？
第二3还是
2
2跟 field 有关系没？
的 field，
没不重要吧？那个 field
OK，
应该不重要吧？你怎么不要 try 你那个0跟1的东西
啊？
因为不要 try 你刚才讲的，
因为我想了，没有
有出问题没？
没有
出问题
考完。
为什么？
就是好像我如果有一个方法是有 S1 到 Sn， 然后我每个都要 S1 加 Sn 啊，然后这样子我有可能出来这个 SND 因为全部人都
消掉？
会抵消掉。
你是说做出来的东西会被另外一个东西干涉掉？
但是呢
New example。New example。
example 想一下
啊，你 try to work from example， 把它弄掉。
就好像
OK，
是
我要开始先，等下再讲。Okay, let's continue. Okay, so just now, Joya asked a very good question. If you just purely look at this argument here, if you just replace with NEF, right? NEF will satisfy this because I just mapped it into Z, right? But the point here is what is closed in Zariski topology mean? You are an affine algebraic set. But what does the affine algebraic set mean? The equation that you get equal to 0 must come from a polynomial. Okay, so if you have polynomial composed with polynomial, then you get a polynomial. So this is the point. Right, last time we showed that y equals to sine x is not an algebraic. Algebraic, right? It's not algebraic. Okay. Yeah. Okay, so maybe for some of you, acting on a function, giving you a function is a bit risky or confusing. But you really need to think of these function as some element. Just some element. Okay. So that's why you learn topology. Topology treat anything as a point only. Point set topology. No matter it's a function space or any affine space vector space they are all point, just point. So that's why you learn general topology. Okay. Okay. Right. What's the next thing we're gonna do here? Let's go a bit faster. So next proposition is if you start with, so just now we say that I give you a polynomial map, then you will have a K-algebra homomorphism by this pullback. So now is if I start with a K-algebra homomorphism, okay? If I start K-algebra homomorphism, then actually we can work backward, you know. From this K-algebra homomorphism, we can find not just one, but a unique one. Okay? A one unique polynomial map. Polynomial map F V to W such that phi equals to the pullback of F. Okay, we can work. Actually, it's unique also. Okay, not just existence but also unique. So now your job is how to find it. Okay? If I tell you that there's a map between this coordinate ring here, okay. So how should we do this? Yeah. So if I give you a map between coordinate ring, how to cook up a polynomial map? Okay, such that it works. So in this case here, we got V to W also. And then I tell you, so let's say this one going to A1, there's a V going to A1 also. And then I tell you that I know how to go between, let's say this one is V1 here, V2 here. I tell you I know how to go between this two map. Then I actually can cook up this F. And then there's a unique one. Okay. Just now we start from F, right? And then I tell you how to go from V1 to V2. Now is I tell you there's a way to go from V1 to V2 and cook up this F. So meaning what? You need to define a map from V. Okay? You need to define a map from V. Okay. So how on earth we're gonna do that? Okay, how on earth we're gonna do that? Well, so let's do it. So prove that. Suppose W live in some affine space. Okay. And let Y1 up to Ym be the coordinate function. Okay. So once we have this coordinate function, right, really we can write down our coordinate ring now. Okay. So this KW is just generated by this coordinate function quotient by the ideal attached to W. Right or not? Okay. So in other words here, this is a quotient ring, right? Well, you can consider the coset of Y1 up to Ym here. Okay. It's generated by this coset. Okay, makes sense. Okay, so where this yi bar is equals to yi plus I. Make sense or not? Okay, so how do we define Fi then? Okay, so you want to have a polynomial map, right? From potentially, let's put it as from the AN affine space to the AM affine space. Okay, so you need to define what are the Fij here, Fi here. So one obvious thing you can try is, how about just let our little phi here add on these coset. Okay, then obviously this is a map from where to where. This is a map living in KV. Correct or not? Right? Because the image of 5 live in KV. Okay, phi is a map from KW to KV. So the image of 5 should live in KV. Okay, so for OI. Okay, so if we define this, what do we need to check here? What do we need to check? Okay, then what's the whole picture here? Then we will say that this f defined by this f I, right? From V to AMK is a polynomial map. Why? Because we already write it as a component of polynomial map now. Okay, polynomial function. Okay, so this is a polynomial map as described in the previous lemma. Correct or not? Because each of them, they map from where to where? They map from V to A1K. Okay, so if you put M of them together, then they map to AMK. Yeah, no? But now is, do we really map into W or not? Okay, so are we mapping into W? Well, first, we need to show that the image of FV is really living inside W. Living inside W means what? W is what? An algebraic set, right? So you must be Q by some polynomial. So you need to show that the image of this function also vanish under this polynomial. Okay. So to see this, suppose that G equal to G y1 up to ym, and living in the ideal attached to this W here. Okay. Then what? Well, if you consider these G on this coset, right, it should also vanishes. Alright, now you just add some IW stuff in. Okay, should vanish also. So let's look at this G on all these images Fi. Okay, but how do we define this Fi? This Fi is really images of the coset Yi. Okay, but the important thing here is, what do you hope for? What do you hope for here? When you see this, you know G on Yi bar are 0, but here in middle got a phi here. So how? What do you hope for? You should hope that you can pull the phi out. Okay, so actually you can pull the phi out. Why? Anyone can explain why we can pull the phi out? Why we can pull the phi out? G is a polynomial. Phi. Why can we pull the phi out? Phi is the K of your model that. Can you say loud? Hey, what your sentence? Your sentence haven't finished. I know. Yeah, try say a full sentence. Why? Why can we pull the phi out? So if we can pull the phi out, then actually we are done. Why can we pull the phi out? Huh? Say again. Say again. Why can we pull the phi out? What is phi? If you don't know phi, how do you know whether it can pull out or not? What is phi? Phi go from where to where? KW to KB. G is a perfectly good element in KW. Okay. And then, so, well, if you look at this map here, this phi here should send G in here to phi G. Right. And then, any idea? Okay. Leave it here first. Next class, you tell me why. Tell me why it works. Okay, next class, you tell me why it works. Huh? Okay, how about the last part here? So next, we have to show that actually the pullback, the thing we created is phi actually. Okay, so how do we prove this? So we see that actually the elements of y1 bar and ym bar actually generate kw, right? Just now we write it out already. So it is just enough to check on these generator. Okay, so just enough to check on this generator here. But how do we define this phi y1 bar here? But this phi y1 bar here, how do we define it? So let's check. So how we define fi here? So we define it as phi y1 bar is actually equals to fi. Okay. So are we done yet? I think we are done. Okay, let's draw this. So we want to show that this V is going from V W, and then now to show that it's enough to show that this Fi here is equals to F star on Yi. And then what are these yi bar doing? This yi bar is a map going from W to some A1. Okay. And then where's our F here? Our F here. So our F here is going from, so F here is defined to be phi of y1. Correct or not? Let me see. F is from B to here. Okay. Let me check. Oh, so okay, a bit confusing here. So here, actually, we define this F to be F1 up to Fm here. Okay, where these Fi is defined to be phi on yi. Okay, I think this is good. Okay, so what we're going to show is we're going to show that phi yi bar equals to phi star I bar using this Fi here. Okay. Is it true or not? The first one here is by definition. This one is by definition.
Okay, so how about the second one? So you got your F look like this, then you got yi bar look like this. What are you doing here? This is the coordinate function, right? You just read out the Fi. Correct or not?
Correct or not? So so if you do F and then you do yi bar, what do you get? You actually get Fi. And what is this? This is by definition F star on yi bar. Okay or not? Excuse me.
Right. So this part here, what is this? What is pullback again? Pre-compose or post-compose? Pre-compose, right? Okay, so you do F first, and then you do Y. Okay. Y bar is the coordinate function, right? You should read out the I coordinate, which is y. Okay. So you can see, this step here is a unique construction here. Because if you have other F appear, right, they should agree on every coordinate. Okay, so it's unique. Does that make sense? If you have other G, let's say GI, GM, and so on, they should agree here. Okay. So that's why it's unique. Okay. Because unique by this construction here, phi of this coset. Okay. Because this is how we define this F. Okay or not? Okay. Okay. So we have done the proof. So the corollary is there's a bijection, okay, with any polynomial map. And the K algebra homomorphism. Okay, so what's the projection here? We send F to its pullback. Okay, and then we have if you have a K algebra homomorphism, we can construct a polynomial map for you. Okay, so then you can define what's the isomorphism of polynomial map. What do you if a polynomial map is an isomorphism, if what? If it is invertible.
Okay, so there exists a G such that HG is identity and GH is identity. Okay, so if we talk about isomorphism here, then we can talk about isomorphism on both sides. Okay, you will have an isomorphism of algebraic set. Okay, if I only have if the pullback is the isomorphism of the okay, you can prove that. Try and prove it as a very good algebra exercise. Okay. Any question? Any question or not? Okay, so I give you a last sentence here. Corollary, a polynomial map F from V to W is an isomorphism of algebraic set if and only if the pullback is also an isomorphism. Okay, so this proof is quite easy. So how do you do? We know that the identity is what? Identity on, let's say, KW, let's say KW is equal to what? The induced identity on W, which is what? Let's say we are going from W, right? How about go from, okay, go from W lah. So G going backward, no? So how to go from W then? So GF, correct or not? G start from W to V and then V go to W. Okay, so identity on a star is FG star. Let's say F is invertible. This case we call GF inverse to save your energy. Okay, so but what's the pullback on the composite? It's just add F inverse dual on F dual here. This means what? This means what? F is also invertible. You have a function that composes like it. Okay, so you do both sides. Okay, this one is on the W side. You need to do the V side also because left right. Okay, does it make sense? Okay, so you see, this proof follows from the functoriality. Okay, functoriality. How to split the pullback. Okay, the functoriality. Okay, well, should we give some examples? So let's give some examples. So first example you will see is this map here. Let's say we have a parabola curve. Okay, in A2, let's say go to A1 here. What's this map we want to consider here? Just send x squared to x coordinate. I read the x coordinate only. Okay, the claim is you have the polynomial inverse here. You have an inverse here. What's this inverse? You need to go backward. So meaning if I give you S, can you reproduce a whole curve or not? Can or not? Can you reproduce the whole curve? So we got a line like this, right? Y equals to x squared. I project it down to x coordinate. Okay, can you produce the other curve, the other point or not? Huh? What's the inverse? You know what's the domain, codomain? Going backward. So phi inverse go from where to where? A1 to A2. Okay, so you need to give me a 2 coordinate. Send T to Tn T squared. Okay. Okay or not? Tn T squared. Does it make sense? Isaac, 很 blur 很 blur OK 吧？我每次看到你有点担心，你知道吗？ 那就讲一些没有很难的东西，但是你就很 blur，我不知道怎么办啊？没有，你要问，你知道吗？你要问啊，不然的话我不知道你做我，因为我不知道你 blur 在哪里，有点困扰。But anyway, so what do we have here actually? So we prove that there's a isomorphism of varieties here, right? Okay, so actually this line here is isomorphic to A1. Okay, makes sense, right? 这条线就是一个 affine line, one affine line in A2. Okay, makes sense or not? It's just a line. It's just an affine. Okay. Okay. Next. Well, I mean, in a linear system, right? For example, yesterday we roughly talked about, right? So you can define invertible matrices, okay? B and invertible matrices. Then the thing you study in the linear algebra says what? The system of linear equation that formed by this matrix, right, should have a solution. Okay, but in our context, right, this linear map here, I mean, we will see it as a bijective polynomial map. Okay, from where to where? Okay, from where to where? Let's see, so actually this is just defined by this yi here. Okay, from an to an also. Must be an to an because we talk about invertible matrices on square matrix. And must have the same dimension. Okay. Another thing is, I think this is the same already. Oh, right. Right. Very good, very good. So let's go back to this a bit for a while. So just now we said that if you have a isomorphism between variety, you will have a isomorphism between K algebra, right? Okay, so what's the K algebra on this both side here? What is the K algebra on both side here? So this is, we call it phi already, right? Okay, so let's see, is it the correct function we want to consider here? Wait, so phi inverse. So let's look at phi inverse star. Okay, phi inverse star go from where to where? Opposite, right? So phi inverse star should go from v of y minus x squared to, let's say, k of a1 here. Sorry, not just this v here. It's a k of this guy. Okay, so go backward, right? Phi inverse should go backward. Sorry, pullback of phi inverse should go backward. From k adjoint, not k coordinate ring on this unit, on this parabola going to the coordinate ring of A1 here. Okay, so what's this two coordinate? What's this two coordinate ring? So I think KA1 is obvious, right? This is just K adjoint one variable. The other one, K adjoint XY portion out by Y minus X squared. But this one is isomorphic to what? Kx. Okay, so you can check that. What does this pullback do? Is just sending X to T. It's also an isomorphism. Why? What's the inverse? Take T sending back to X. Okay, so you can actually check that this pullback send X to T. Okay, how to check? You just check of generator. Check of generator. The generator here is X. Yeah. See what does this when you compose pre-compose or post-compose? Pre-compose, right? You do X and then do phi inverse. it should get you t。不相信我啊？要试一下，要试一下嘛？啊，要不要试一下？不相信我。So phi inverse star on x 这个 function, what do you get? You get x and then pre-composed with phi inverse, right? Okay, but phi inverse go from where to where? T to t squared. Okay, so you get, so, well, you need to check function, right? So phi inverse, take t, wait, let me see. So you do x on phi inverse, right? Correct. Okay, then what do you do next? This is definition, right? Okay, so what do you do next? You want to check it on this ring here. Okay, so you need to compose this everything with a t. Okay, you need to check where it sends t to. But where it sends t to, it sends it to compose x acting on t squared. But what is x? You just read out the t. Correct or not? I think so. Yeah. Okay. 对吗？应该没有错吧？ Okay. Okay. Next, we show this one. Let me see. Let's show you something interesting one. Okay, let's show you this one. Okay, I think this one is more interesting. So let's show you that one. Okay, let's look at this map here, A1K to C1. Okay, T going to T square and T cube. Let me see. It's good or not? Okay, I think this is quite good. Okay, look at this one. Okay, so if you look at this, the claim is this is a bijection. Okay, this is a bijection. Is this a bijection? Okay, this is a bijection. Can or not? T go to T square and T cube. Can you create T? Take the T cube divided by T square. Okay, take Y divided by X. But you look at here, but what you see is, if you look at the K, the pullback of F, right? Okay, if you look at the pullback of F, the pullback on this K C1, right, is an element in K A1, which is equals to KT. But this map here is generated by F star X, which is T squared, and F star Y, which is T cube. Okay, so what? And so actually the pullback of KC1 here is not equal to KT. Okay? Because it's generated by T squared and T cube. Okay, you can never get T. So actually F star is not an isomorphism. Okay, it's a bijection or not isomorphism. What does it mean here? Actually, what's the inverse map I tell you just now? You take Y divided by X. What's wrong with that? Not that. The inverse map we define, right? the inverse map for the bijection that we define by G from C, from where? What do we call this? C1, okay. From C1 to A1K here. How do we define it? We define it by quotient. Meaning what? Actually, there's one point for this function not defined, which is the origin. Okay, we need to send the origin ourselves. But if we define like this, what does it mean? This is a piecewise function. Actually, this is not a polynomial map. Okay, obviously, this argument is not general yet, but you should also can argue that if phi inverse is a polynomial map, there's some contradiction happening. Okay, so you cannot find a polynomial map. The obvious one is not a polynomial map, and then you need to argue that if it is a polynomial map, the inverse is a polynomial map, there will be some contradiction happening. Okay, you cannot find the inverse as a polynomial map. Does it make sense? Okay, no. Okay, the obvious guy is not a polynomial map. Okay, and you show that all the polynomial map cannot be the inverse of this V. Using some degree argument, I'll put inside the notes. Okay, using degree argument. Okay, any question? To motivate the next part, right? Hey, do you guys need to go back early or not? 有没有人要早回去啊？可以给我上到6点吗？可以吗？有上到6点啊？ Okay. So to motivate the next part, right? I want to show you a video. Let me show you a video. This video is about a breakthrough prize in mathematics. Breakthrough prize. Let me try. Yes. So this year breakthrough prize is awarded to Dennis Gregory. So Dennis Gregory with his collaborator, in particular his student called Sam Rankin, they wrote a 5-long paper on proving geometric length. So what's geometric length here? So basically they try to connect algebraic geometry and representation theory. So that's why you are here to study algebraic geometry. Okay, so make sure you study it well, because there's someone in the department don't look good on you guys. So better you show them you are okay. You understand or not? Otherwise, this course next year no more. No more already. Die. Okay, die in Malaysia. Okay, so make sure you prove them you can study well. I will help you one. Okay, for sure. I'm not here to fail you. 不要传什么谣言说我要把学生 fail 掉，怎么乱讲啊 ？OK， 不要乱讲这种东西。Okay, I'm here to help you. Okay, to pass this course, to learn well. Okay, so make sure you give all the feedback to me. Okay, whether which part you don't understand anything. Okay, make sure you tell me. Okay, so and then this breakthrough prize actually is like an Oscar basically. Why is it like Oscar? Because this is done by Facebook. I mean Facebook and Google, in particular Mark Zuckerberg with his friends. So they invite all the celebrities in. Even there's a show on this event here. Okay, so I will start it. Try and listen how they introduce this Dennis Gregory, and then what Dennis Gregory said about receiving this prize here. So please pay attention.
Greg Brockman.
I don't know about you, but for me, math class was pretty dry. No one told me that beyond the textbook, there were whole unexplored worlds, or that there was such a thing as a conjecture, a way of asking, what if this idea was true? What would it mean? Where could it lead?
In the late 60s, the mathematician Robert Langlands made a series of very bold conjectures. He envisioned deep connections between two seemingly unrelated fields. Others built on those conjectures, and through them were able to solve some great mysteries. Our next laureate has devoted 3 decades to building an extraordinary bridge between ideas.
Once, a land divided. On one side, a place of flowing curves and complex surfaces, rich with hidden symmetries. The other, a zone of abstract, higher dimensional spaces. For years, many hoped it possible to move between them, but the view from either shore remained murky, and often progress seemed impossible. Until Dennis Gatescory, over decades of work, found a way. Designing new tools and technologies, Gatescory and his companions constructed an amazing bridge connecting the two lands, allowing easy passage of ideas between them, and opening the possibility for new bridges to connect distant mathematical realms.
Foundational works and numerous breakthrough contributions, including the proof of the geometric Langlands conjecture.
The breakthrough prize in mathematics goes to Dennis Gatescory.
I want to mention an aspect of doing math, which is kind of obvious to the practitioners, but maybe less so to the world outside. It's actually a social activity. Of course, math relies on solitary deep thinking, but more often than not, it results from and relies on a dialogue. Sometimes it takes two for a tango, sometimes three, sometimes nine. Most of the work for which this particular prize is awarded was produced in a dialogue with Sam Raskin. Here's one piece of advice I'd like to share with people who are starting down this road. You don't have to walk this path alone. Find folks you find it fun to talk math with. Thank you.
Okay, you don't need to do maths alone. Please talk to your friend. Okay, no. If you don't want to talk, then we cannot help you. Okay, so make sure you get help. Understand or not? Okay. So here's talk about algebraic geometry and representation theory, right? So if this course run well, right, I think our next target is representation theory to open a new course. Okay, so these are very, how to say, what's the English word? Contemporary, okay, contemporary research field. Okay, yeah, very hot one, very exciting one. Okay or not? Okay, yeah. I can say I think that video is AI generated. It's very AI generated. But anyway, it serves the purpose, that's fine. Okay. Okay, still got 5 minutes. So another contemporary thing I want to go through you is category theory. So today we're going to define it first. Next time we'll talk a bit more about it. So we'll look at some category property of polynomial map. So the way we introduce category theory is the same how we introduce topology in this class. I will just show you that these polynomials will satisfy some property. And then this property will make up a category theory. It's just like your ideals or your affine algebraic set. How do you deal with the union? How you deal with the intersection? And then they all put together become a topology, that's all. Okay, so our focus here is not the jargon category theory, but the property that's satisfied by this polynomial map. Okay or not? We don't care about the real the topology, real topology itself, but we care about how you intersect these affine set or taking union. Understand or not? Okay, so we introduce this jargon through the properties. Okay, but before that, we need to have some measure with all of us on the same page. So we're going to define what's the category first. Okay, so what's the category here? So basically, there are two objects here. Consists of two data. Okay, two data. One data is a class of objects. we call it OBC here. Second, for every two objects in the class of objects, then there's a set of morphism. Okay, let's call it morph from A to B. Okay, so there's something that need to satisfy by this morphism. So satisfying the following property here. So first property is for every ABC object of your category. Okay, actually there's a map. Yeah, there's a map. There's a composition map. Okay, from morph of AB cross morph of BC. Okay, to morph of, what do you think? AC. Good. Okay, so meaning what? If I give you two morphism here, we call it morphism, the elements inside this morph here, we should be able to compose them. I didn't say they are function. I just said that they can be composed. Yeah, they can be composed using GF. The way how you compose function. Okay, I didn't say they are functional. I just said that something called morphism. Okay, but behave like the function you know. What else you know about function? What else you know about function? It should be associative. Okay. So meaning what? If you do GF on F, is equivalent to doing F hash first and then G. What else you know? Identity function. Okay, so we should have a guy called identity here. Okay, so for every A in your object, we should have an identity morphism. Okay. So what does this identity morphism do? It should satisfy what? If you compose to the right or compose to the left, you should get the same map as you started with, where this F is an element from maybe morph of A to somewhere else, B or G is from somewhere else back to A. Okay, so this morphism should have composition. The composition is associative, and then you have a identity. That's all. Then you got a category already. So how many category you have seen before? How many things satisfy this kind of property here? So first thing you come into this university, what you learn is the category of set. Okay, what's the morphism set you consider here? Set of the map of set, function of set. Okay. And then second thing, if you do discrete math, I think your discrete math is different from the service course one. Service course have graph theory. Okay, so if you know a little bit of graph theory, we can talk about the category of quivers actually. Okay, so what are the object and maps here? Vertexes is your object. And then how to go from vertexes, these are the path. Path also associative, right? There's an identity path. What's the identity path? The constant loop, the constant path, which is the vertex itself. And then first year very headed one, the category of vector space. Okay, what are the maps here you consider? Maps between vector spaces. These are the linear transformation. Okay, the morphism set you can consider as a linear transformation. Got identity matrix, right? Associativity, right? You compose, okay, your matrix. And then you go to second year. Second year, what did you see? Category of groups. What's the map here? Group homomorphism. Group homomorphism. And then in the same course, you actually also see the category of ring. Okay, which you consider as a ring homomorphism for your Holmes set. And then in this semester, I think most of you learn the category of topological space. What are the maps there? What are the natural maps you consider there? And what's the thing we have after topological space? We just consider continuous maps, okay? Because it extends open set. Okay, I cannot say it extends open set to open set, but there's a relation, okay, that you can check using this continuous map on your open set. And in this course in particular, what we're gonna learn is the category of affine algebraic set. Okay, at least in this section here, affine algebraic set. What are the map here? What are the map we keep talking about just now? Polynomial map. Okay, and then what we're gonna show you later is this category is the same, okay, equivalent category with the category of finitely generated reduced K-algebra. I think we have introduced all these words to you, right? Reduced algebra yesterday. Okay. What are the maps here? These are the K-algebra homomorphism. Just now we already played a little bit with K-algebra homomorphism. Okay. In the next class, I will quickly introduce to you the equivalence between the last two categories. We won't test on this. It's just a concept for you to digest. Yeah. Any question before I finish? Okay, if no question, we'll see you next week.